build the diffusion operator. We have the oracle, so the operator we built before. Wait, we have a message from the chat. Okay, they can hear me. Good. That was able to mark the correct solution, the target, the guilty guy, the one who put the coffee, the sugar into the coffee, flipping the amplitude of the target state. Now we need to amplify the amplitude of the state because, as Stefano was mentioning, if we try to perform measurements of the state like we are doing with the number of shots we defined, you will see with this kind of configuration you still see the superposed state in terms of amplitude because you are elevating, or squaring, not squaring. Yes, you are, I mean, it's positive, positive definitive. I don't know how to say in English, but you know. Okay, now we need to implement the tool which is able to perform the amplification of that state. So let's follow the same convention we defined before. So we define a function, we build a circuit, and then we return the circuit and we sum the circuits all together. So a function which we can call build diffusion operator, and we just need the number of qubits n. Because the diffusion operator is not depending on the target state, like the oracle, we should know which is the state. The diffusion operator needs just to perform an inversion with respect to the superposed state, like we were showing in the plot with the sphere. So we set up the circuit with the same number of qubits, n plus 1. Then we add, okay, this step is not really necessary in terms of probabilities, but is necessary to preserve the mathematical definition of the diffusion operator. We are going to apply an X gate to the ancilla. This will just change basically anything. We are swapping the ones into zeros for the ancilla. But in terms of amplitudes, we are not doing anything. Okay, it's just for preserving the convention. The same result you can get if you don't do this, but it's more complete if you do that. So we need to add a gate, which is X to the ancilla, which is the qubit number n in the sum. Okay, when this is done, we need to apply again a flip, but with respect to the superposed state. So in this kind of setup, you probably will complain that we couldn't understand very well what's going on. We have another notebook in which we built this diffusion operator step by step, and we see to the amplitudes what's going on. If you want, then we can have a look to this. But right now, what's happening is that by applying some Hadamard gates and applying some multi-control Z, we are able to flip around the maximally superposed state. So this is quite mysterious, can be mysterious, but if you want, again, we can open the black box later. What you need to do is to implement a layer of Hadamards to all the qubits, and then a multi-controlled Z that can also be implemented by applying a layer of X gates and a multi-controlled X. It's the same in terms of implementation. This is more hardware-oriented. For this, we do this in this case. It's compatible with the hardware execution. So for Q in range N, because we want to apply these gates only to the input register, to the system, not to the ancilla, we say circuit.add gates.h, the Hadamard I was mentioning. Okay? And then we need the X gates, circuit.add gates.x to all the qubits. At this point, we prepare the state to the multi-controlled gate. And we add it. So circuit.add gates.x, multi-controlled NOT gate. We apply the gate to the ancilla, so the qubit is the number n. Oh, sorry. Can you see now? Okay, sorry. because I see the whole screen and there is cut it. Okay. And the qubit, the target qubit should be the ancilla, so the n. And we need to control this operation with all the other qubits. Because again, we want to, in some way, activate some phase flip on the system. But now this flip has to perform the operation of flip around the superposed state. This is done by this implementation indeed. Controlled by. And all the qubits in the input register. So range, again, the Pythonic way to write down the list of length n. Then we need to repeat the layers. So we need to reapply again the X gates and then the Hadamard gates. So for Q in range n, again, circuit.add the X, gates.xq, and then circuit.add the Hadamard. We are restoring the original configuration of the system by reapplying the superposition. Okay? Finally, we return the circuit. Okay? Okay. This is supposed to act like a diffusion operator. So what we want from this is a final state in which the amplitude of the target is amplified. Let's see what happens. Now we have all the tools. Okay? We have the initial layer, we have the final layer, we have the oracle, and we have the diffusion operator. So we can build the Grover algorithm, the full Grover algorithm. So let me write down another function. Question? No? Okay. Another function in which we apply all the operations sequentially, okay? So let me call it def build Grover. We need to provide this function with the number of qubits again, because we need to define all the components inside, and the number of steps. So the number of times we want to repeat the couple oracle diffusion operator, and so on. So the circuit has to be circuit, as usual, a circuit composed of n plus 1 qubits. Then we should prepare the state. Okay? So we need to apply the initial layer. Let's comment here. We can do that by saying, okay, C plus equal, which means I'm summing to see what is coming on the right of the equation. Build initial layer with n. At this stage, we prepare the initial superposition and the ancilla is in the minus state. And what we want to do is to repeat oracle diffusion operator as many times we want. So for our iterator loops over in range n steps. Typically we use, I don't know if you know this notation, but we use underscore where when we don't explicitly make use of the iterator in the code. So we are just not saving the variable. Okay? And then we say, okay, circuit plus equal the oracle. So build oracle. And for building the oracle, we need to provide the function with the guilty index and the number of qubits. So guilty index and n. This follows the definition we did before. And then we also need to add to the circuit the diffusion operator. With diffusion operator, it needs just the number of qubits n. Okay, we are mostly done. We just need to add the measurements. So we say C plus equal build final layer. Again, we need the number of qubits. And then we can return the circuit. It's clear so far? Okay. Let's check what happens. We repeat the Grover iterator once. So we apply Oracle diffusion operator. So our circuit will be build Grover. And we need to provide, you remember, the number of qubits and the number of times we repeat the experiment. So 1. And then we can draw the circuit. So let's have a look to the diagram we have here. Again, to check if everything is correct. We have a first layer of Hadamard on the system, plus the NOT operator and the Hadamard to the ancilla, initial layer. Then we apply the oracle, which is composed of some x, depending on where we want to flip the 0 into a 1, the control NOT operation, and then again the x. And finally, we have the diffusion operator, which is composed of a layer of Hadamard, a layer of x, multi-control NOT, x, Hadamard. And finally, we have the measurements. So everything should be fine. Seems to be what I wanted to see. And now, we can print what's going on with some output. So we can call again, yes?
In the last function,
yes.
you used good index, but it wasn't defined inside the function, didn't it?
Yes, because we defined it before in the notebook. Yeah, in principle, in a more elegant way, you should pass also the guilt index. Yes, yes. In this case, it's already defined because we did it before, but yeah, you are right. We can do that, by the way. Okay, so now we go to print the Grover probabilities. In this case, we use a function which is from plot scripts. We call plot Grover probabilities. And again, you should pass the circuit and the number of shots. So what you see from here, okay, is that in the end, after one Grover iteration, the probability associated to the target state, which is the guilty one, is increasing already. But ideally, this is not enough, because you see a lot of, a good quantity of the probability, the 75%, is still stored in the other components. So if you go on in your lab, you perform one Grover iteration with 5 qubits in the input register, and then you say, okay, I'm fine, I just measured the final results, I should check and detect my final correct state. You will be 75% of the time wrong. So we need to repeat Grover. And we need to repeat the oracle and diffusion operator an amount of time which is proportional to the square root of m, if the theory is correct. So let's try to see what happens if we repeat this Grover with 2 steps of Grover. Again, we build our circuit, calling the function which is build Grover. And we need to provide it with the number of qubits and the number of steps, in this case 2. We draw the circuit. And as you can see, we have the same pattern, but repeated twice. Now we plot the probabilities and we see what's going on. So, plot script dot plot Grover probabilities. We need the number of qubits and the circuit, and the number of shots. As you can see, the probability of the target state before was 0.25. Now it's 0.6. So we have this 60% of the possibilities to get the correct solution. Is this enough? Yes or no? No, because you have 40% of the probabilities to get the wrong solution. So ideally, we want to have something very close to the 100%. So now, let me see what's going on already. Okay, so we can maybe do a little study of what's happening with the amplitudes to see, in the end, we are detecting the correct person. Let me collect the frequencies from the execution of that circuit. So we execute the circuit, C, with the number of shots, for example, equal to 1,000. And we call the frequencies. So we are simulating the collapse of the wave function. Now I want to create what we are doing inside the function, thanks to which we are plotting, we are reconstructing the empirical probabilities using these frequencies. You can do that by defining a vector, probabilities, a list, sorry, probabilities. And then we say, okay, for bit string in bit strings, in frequencies, because as you remember, the frequency is a dictionary in which the keys are the bit strings, okay? So for bit string in frequencies, okay, what we do is just to append to the probabilities the number of times that bit string came out, okay? So frequencies of bit string. This is the number of times we got this specific bit string, okay? Divided by the number of shots, so we reconstruct the probability. Okay. Then what we do with this is just to compute the name or the index, if you want, corresponding to the highest probability in the set. So we can say that index is equal to np.argmax, which is detecting the maximum value in the array or in the list of probabilities. And so now we have the index. Let's print it. And the index is the one we defined at the beginning of the lecture. Let me zoom a bit. Okay. If you want to be a more verbose, we can use again the f string, so we can say print f, and we say the guilty state, so the guilty component is bit strings of this index, okay? And or corresponding to our guy, which is names of index. So we are going in the right direction. The correct state is detected to be the one with the highest probability, which is still 0.6, not enough, but we are on the right direction, which is corresponding to the 01011 state, and David Daniels, that was the guilty guy, the one who put the sugar into the coffee. Now, from the theory we know that the number of iterations should be ideally proportional to this number here. We proved it before. So let's see what happens if we repeat Grover this amount of time. Or better, let's see what happens to the maximum probability we are computing here, increasing the number of Grover iterations. I want to see after this that in some place next to this value, we are going closer to 1, okay? So, let's compute this number. The optimal number of iterations is the pi divided by 4 times the square root of 2 to the n, because it's the number of solutions. Let's print it. So in this case, printing this number, we know that ideally we should perform a number of iterations, which is 4 or 5. Okay? So let's repeat Grover sometimes and see what happens to the probabilities. Let me allocate an empty list that will contain these probabilities varying the number of Grover iterations. Let me call it probability target equal to empty list. Then we define a number of times we want to repeat the experiment. We don't stop to 4. Let me go through like 10 or 15 Grover iterations to see what happens. So n, let me set it to be 10, for example. So what I'm going to do now is to repeat Grover with n steps equal to 1, 2, 3, 4 until 10. And finally, we loop, so for E in range n, we need to create the Grover circuit. So C equal to build Grover. We pass to this build Grover function the number of qubits again, and E, because E is looping over 1, 2, 3, 4, and so on. Even we are not applying the 0, is the case in which we are not applying anything. And then we just do the same I was doing before, but we call a function that's in a utils scripts, which is called compute max probabilities, you see here in the comment. Okay, it's just to speed up this procedure. Okay, so the probability target, we say dot append utils dot, the name is compute max probability, and you need to pass the same things you pass it to the plot Grover amplitude function, so the circuit and the number of shots. So we are appending the maximum probability registered in the vector for a number of Grover iterations increasing from 0 to 10, to 9, whatever. Okay? Is it clear, this step? It's clear? Okay. Let's plot it. Okay, so let me plot some stuff. Now we need matplotlib, so let me define a figure with some fig size. So this is basically what we did in the plot scripts file. Now we are doing it live, but if you open the scripts, you will see a lot of functions like this. So let's define some size of the figure. This is not very important, but it's just to make a size which is nice. 4 by 8, that's fine. Then we need to plot the range of the, so on the x-axis we want the times we repeated the Grover, so we need a range, np.arange you can use, from 1 to n plus 1, oh actually no, because it's 0 also, 0, n, 1. So you are basically storing all the integers from 0 to n with step 1. So 0, 1, 2, 3, 4, 5, and so on. And then we plot probability target, yes, on the y-axis. Let me set some fancy things just to make the plot a bit nicer. So the line style, just a line. We can say the marker size, so the size of the dots in the plot equal to 15. Some opacity, I mean these are not very important things, you can just follow if you like, and some color. Okay, then we add also the line, so plt.plot and p.arrange. Again, I'm plotting basically the same thing just for the sake of having a nice plot, but this is not super important. Prob target, same line style, color black. label. We give a label to this object in the plot, which is Grover iterations. Let me dezoom, maybe you see better. Oh. Oh. What did I do? Okay, fantastic. Then let me plot a vertical line corresponding to the optimal number of iterations, just to see in the plot where is the optimal number. Plot. Opt. Because we save it into the plot, the opt variable, if you remember here. Okay. Then, sorry, this is v-lines, okay, which means vertical line, basically. And then you need to provide this function with the starting point and the final point on the vertical line. So let me say 0 and 1.1, because we want it ideally to go until 1, the probability. Some color, and some label. So ideal number of iterations. Then let me call the x-axis. I mean, let me use the ticks corresponding to the right ticks. It's just to customize the plot. So x-ticks. And again, NP arrange. 1 and plus 1 should be nice. And then we can give some title and some label to the x-axis, the y-axis, whatever. No? So plt dot title. Okay. Some x label, which is on the x-axis we have the number of steps. And one y label, we have the probability. So the maximum probability in the vector. So we should say max probability. Let's plot the legend and show the function. Something is going wrong in the picture, but we are missing the markers. Sorry? Sorry? Yes, because I wanted to plot the markers, and I mean, it's just to plot separately the points and the function. But I mean, it's not important. The important point is you see the line. Okay? Yes? Ah, yes, the marker is missing. The dot. Okay, you see the difference is not so huge. You just see the points. Okay, so what's going on? We know that in the end, the maximum number of iterations seems to be close to the target one, so the ideal one. So let's try to repeat the Grover for a number of times, which is 4 instead of 2 or 1 as we did before. Okay? Are you okay until here? More or less? Are you died? Yes, you are died? Okay. Okay, so we are basically done.
Maybe next step show the your discipline.
Sorry?
More, you can try to put more steps.
Ah, yes. If we repeat this procedure, which is basically using Grover, computing the final probabilities, taking the maximum, and plotting the maximum, you see you start to visualize here a sort of periodical behavior. If we repeat for a higher number of times, like 15, what happens is that you see a periodical behavior for real. So the number of times we have here, that's around 4, the optimal number of times, could be also, I mean, you get the same result if you repeat for a number of times which is like 13, something like this. But of course, it's not wise in the sense that if you are executing on hardware or a noisy device, then you should avoid to do a lot of gates to perform a lot of operations, because the more number of gates you add, the more noise you add also. So it's very important to compute the ideal number of Grover iterations to know where to stop in the algorithm. And this is the same pattern or something similar we started to see with the phase kickback at the beginning of the lecture. So let me repeat the Grover with this number of iterations, let's say 4. Again, we build our circuit with build Grover with the number of qubits and the number of times we want to repeat Grover. We plot it. So this is start to be a big circuit, executing a lot of gates, okay? And finally, let me show what happens if we plot the probabilities. So plot scripts dot plot Grover probabilities. We pass the circuit and the number of shots. And what happens is that in the end, you finally have the probability to get 01011 basically not equal, but very close to 1. So this is the final step of Grover, in which we proved that, okay, thanks to the oracle, which is able to mark the correct solution, and the diffusion operator, which is able to amplify the correct solution, and then if you repeat this procedure a specific optimal number of times, you are able at this stage to take your system, you perform the measurements, and with probability close to 100%, you will get the target. So in the end, we will know who is the guy who put the sugar in the coffee. So in all of this. More or less.
So there are mistakes,
yes.
possible mistakes in the justice.
Yes, that's a real example of life, indeed. Okay? Yes. Yes. If you go to the lecture 5, you will see a series of cells. We upload probably this evening also the lecture 5 already compiled, already coded, in which basically you can customize this oracle and diffusion operator, stopping the diffusion operator, for example, only to the Adamarts or only to the Adamart plus X, Adamart plus X plus the multi-controlled gate. And you will see the effect on the amplitudes. And so you will see why the diffusion operator built like this actually amplify the correct solution. If you want, you can have a look to that, and then maybe tomorrow, since we are already at 6, we can discuss if you like.
Yeah, no, I have here, I mean, the last cell, the 52, I have included a summary, So you see, we have a circuit there for 34, and the total number of gates is 116. So realistically speaking, if you wanted to deploy this on a real hardware, you might have a lot of troubles because the circuit is extremely deep, So you should be careful with the relaxation times of your chip, the coherence that we might have over time, because it's not easy to get a stable system able to execute 46 Hadamards and 69 X Paulis and provide you reliable predictions. Okay. So what we are doing here is nice, but again, from a hardware perspective, there is a lot of work to be done in order to be consistent and use this algorithm in practice.
One of the solutions, not a definitive solution, to the noise will be the error mitigation that we will see tomorrow. So if you aim to run something like this in a lab, it's a good practice to take into account error mitigation in any situation. But tomorrow we will talk about this. We have a question, sorry. No, okay, perfect. Any question from Zoom or from here? Yes.
When we run any code with any quantum language, in our usual computers, we don't have any time improvement
Yes.
You actually take longer than using a classical algorithm.
Yes, the question is if by simulating these kind of things, it's still slower than the classical counterpart because we are simulating the quantum computer. Yes, in some sense, of course, yes. Because for doing this, we are doing matrix multiplications, and yes, of course, that's true. Yes, except if you go through a different simulator, which is called Clifford simulator. In that situation, you know more things about the gates. You are using specific gates, which are gates unitaries in the Clifford group. And in that situation, you are able to simulate very, very fast. And that's a very specific, would say, regime of simulation, which is very useful, but also limiting because you can do only some things, but it's very useful to do some kind of state tomography or studying the state or doing also error mitigation, as we will see tomorrow.
But you don't have any improvement of the time of computation.
For the Clifford, yes, a lot.
You have
Yeah. And also you can simulate up to thousands of qubits, hundreds of qubits. Yeah. But we are speaking about a very different kind of simulation in this case. If you want, we can provide you with references about this.
Okay. Any other question? Comment? If not, then see you tomorrow.
Okay. Yeah, see you tomorrow.